Good afternoon, everyone. I hope you guys are doing very well. In the previous lectures, we discussed about basic idea for object-oriented software systems development, where we fairly got good idea about classes, objects, packages, for example, and different abstractions, hierarchy, and some basic concepts. Before moving forward in detail, it's a good idea to discuss about UML, which is a de facto standard now for modeling complex systems. Um, it may not be software only, but it can be, this modeling language can be used in many other applications. It's basically a modeling language. How can you model a complex system? That system may be software system, maybe wireless system, maybe any other engineering system. All right. So let's talk about something. We're gonna go little history and then basic overview about UML in this lecture. And in following lectures, we're going to be discussing individual concepts in more detail. So UML, as it stands for, it's a unified modeling language. Unified modeling language, well, the word unified came from the unification of different modeling concepts which were popular at that time. So the idea for UML is that it is a language to analyze, specify, and design software systems. So that's the basic main objective. In 1990, at Rational Software Corporation, three main scientists, Booch, Rumbug, and Jacobson, up to my knowledge, they were working on modeling techniques, and everybody got a little different idea about modeling, and in the end they combined different modeling techniques into one modeling language, and they came up with a unification, and um, it turned out to be unified modeling language, UML. So it's the same way of unification as you might have heard or read about string theory. There were so many concepts, theories were popular before the M theory was proposed, or the idea was given by Edward Witten that basically it is the same thing in a different form. So the unification happened. In the similar way, you can think of there were different modeling languages, they were saying same thing but in a different way. And finally, these three scientists, well, there might be other people involved, but that's what in literature name comes about these three scientists, that they did quite a bit. Um, they worked in the area of unification of different modeling techniques and came up with unified modeling language. So what essentially is that that we have the models and different kind of views, okay, and again the models, or basically the diagrams, we can have static, dynamic, or in other words structural and behavioral diagrams. That's about it. And in the end, if you see from a very abstract level, what is UML? Well, you are analyzing a system and you are drawing some diagrams to understand what different components or what different pieces in a system are doing, how they are communicating with each other, and it's a more formal approach of laying things down so that other people can understand and the whole team can work on to different pieces, and somebody in the end is aggregating all those different components together to build a complex system. So we need a certain modeling tool or a certain way which goes all the way from the concept up to deployment. All right. So we might have different abstractions at different levels, okay, and at all different levels we need some sort of unification or some sort of smoothness, so that the information is transferred from one guy or one engineer to another engineer is transparent, consistent, and we don't make mistakes. All right, so that's the idea behind many things what we do in engineering, right? The word unified means, well, there are different meanings. For example, across historical methods and notation. So for example, let's say you have developed some model and you are using some notation in, you know, um, previous versions or different modeling technique. So is there any way we can come up with a superset which combine all those things together, all those methods and notations across development life cycle? So we learned about software development life cycle. For example, in the very first lecture, is there any modeling language which goes all the way from the concept to deployment, okay, across application domains? Let's say we are talking about now developing software for a game, and tomorrow we can think about developing software for a wireless system, okay, or any other system you may think of, database systems, whether there is any language which can be modeling language which can be applied across different domains, different application domains, okay, across implementation languages and platform. So as you know, we have many languages, many programming languages, many platforms, web development platform, for example, enterprise resource planning softwares, that different platform, um, C++, Java, or Ruby on Rails and whatnot, a bunch of plenty of languages and platform available for development. Okay, so is there any modeling language which work across uh, different implementation methods without loss of transparency or loss of data? Across development processes, we may use different processes for development across internal concepts. So that was the basic idea came when scientists discuss about how do we do that? Is there any way we can unify? So they combine different concepts from different domains, and UML, it started and becoming a standard slowly. Okay, so we are so right now it's UML 2.0, as I know. You can, if you want to read in detail, you can always download the language reference manual UML 2.0 for learning in detail. All right, now let's get a basic overview about UML diagrams. Remember, UML is nothing but you're gonna be doing bunch of diagrams. Okay, it's like an architect, drawing many figures, bunch of figures, um, which makes sense. In the same way, think about, you are a system designer. You got to transfer the information what is in your mind to others. Diagrams is a beautiful thing. Like you go to classroom, professor explains certain things and they draw diagrams and you can understand easily. In the same way, for modeling, UML provides different kinds of diagrams with a different notation, different structure, right? So basically you can categorize UML diagrams in two categories: structure diagrams or static representation, okay, and dynamic diagram or behavior representation. Okay, it's like static means okay, you are John, okay, and everybody knows you are John. You have your certain height, okay, certain weight. Those are static attributes. Now you are running, okay, so that is a behavior that, okay, you love to play uh, games, you love to run, and that's your behavior. So there is a uh, uh, dynamic activity involved in that. So how would you represent? So those different kinds of broadly you can classify diagrams in two different categories. What are structural diagrams? For example, we have package diagrams, class diagrams, component diagrams, deployment diagrams, object diagrams, composite structure diagrams, right? We learned about classes. So basically the concepts which are represented by class diagrams, for example, association, class, interface, different concepts. In the same way, package diagrams, say for example, you have multiple classes and you want to put in one package, okay, and different concepts associated with package diagram, let's say import, export, profile, okay. And in the same way, different concepts for deployment diagrams, so dependency, node, artifact. You can also say that composite structural diagrams, that you combine all different structural diagrams and you make a very simple overall diagram. So the UML is nothing but you will play around with bunch of diagrams, individual component diagrams. Those are depicting basically static information about certain thing, okay, about certain part of the system or certain parts of the system. So the essential idea here is that the things how they are, okay, static or structural. That's the basic idea. Second is behavior or dynamicity or dynamic behavior. Those are use case diagrams, activity diagrams, state machine diagrams, and different concepts associated with these diagrams. For example, state machine diagrams, let's say this component of a system is in which state? Is it in, let's say, coffee machine, okay? Coffee machine can be on state, off state, and working state, okay? That sort of thing, okay? So those concepts. Activity diagrams, action, like say you are running in east direction, okay? Who is controlling your run? Probably you are wearing a smart watch and that is telling you, okay, you are running too fast or you are running too slow. So you have given a control in the hand of that smartwatch, or you may control that smartwatch, okay, now I'm running at this speed, and um, or you go to gym, you run on treadmill, okay, and you control the machine, has to uh, show that behavior, how the control is working, right? Interaction diagrams, how different components are interacting. And interaction diagrams, you further classify them in sequence diagrams, communication diagrams, um, interaction overview diagrams, and timing diagrams. So as you can see, we have in UML, it's nothing but we need to understand the concept behind all these diagrams, okay? So when we understand all these different concepts, it makes our life easier to analyze a complex system. And if we can analyze a complex system, we can basically um, you know implement it efficiently. So thank you guys, that was a very short discussion about UML diagrams, and thank you for subscribing and your wonderful comments. Those who have not subscribed, please do subscribe.